The second part of section 4.3 is going to focus on the graphs of logarithmic functions. So we spent a lot of time looking at exponentials. Now we're going to look at logarithms, and this shows that they are inverses. The blue one is an exponential, where the base is greater than 1, an exponential growth. The logarithm is just the reflection of that. So the domain and range switch. So these are opposite of what they were on the exponential stuff. So the domain is anything 0 on or bigger than 0. The range, though, is infinite. The logarithmic graph, the red one here, goes down to negative infinity, and it forever climbs. Slowly climbs, but it still climbs. The exponential had a horizontal asymptote of the x-axis. The logarithmic has a vertical asymptote of the y-axis, where x equals 0. And where the exponential hit at 0, 1, the parent logarithmic will hit at 1, 0. And the change in the base number is just going to slightly change how curved it is, but they all have the same basic shape. So let's do a table here and graph one of these. So if I put in 1 over 4 to the third for x, the log base 4 of 1 over 4 to the third. Again, think, don't need that right now. Think about the loop-de-loop. The number that I would raise 4 to get 1 over 4 to the third would be -3. If I put in 1 over 4 squared, the power that I raise it to would be -2. If I wanted 1 over 4, -1. If I wanted 1, that's 0, 1, 2. So now I'm going to graph these. Now realize the x's here at the beginning are incredibly tiny. So if I say, I don't know, right here is the number 1 on the x-axis. Oh, that looks terrible. Come on. If that's the number 1. 1 over 64 is obviously going to be almost over nothing to the right, but then down 3. So some dot pretty close to the x-axis, excuse me, to the y-axis. The next one's not going to move over much. That's 1 over 16, -2. I'll be over just a fuzz more at -2. 1 over 4, so over a quarter. I'm down 1. Over just a little bit more to the right, but not much. I hit at 1, 0. And now I jump all the way to 4 on the x-axis. So 2, 3, 4. I'm up at 1 on the y-axis. And then all the way over at 16, so we'll just say over here is 16. I'm up to 2. So it's going to grow. It's going to get taller very slowly, but it does keep getting taller. Oh, wow. Yeah, something kind of like that. That just gives us a feel for what the logarithmic graphs will look like. On number 6, we're trying to figure out a function that will match this graph. Notice these are all logarithmic functions. And all of these have a fairly simple structure, if you will. They're all going to be of the form y equals log base something of x. Our goal is to figure out what is that something, what goes in there. So let's think of these as doing the loop-de-loop, because I think it's easier to think of them in terms of exponentials. So what we're saying is some question mark raised to the y is going to give me the x. So for 6a, something to the y here is 1, the point they give me is 5, 1, is going to equal 5. Well, fairly simple. Something to the first power is 5. That something has to be 5. So the question mark, which again is the thing we're trying to find, for this one is 5. So this answer would be log base 5 of x equals y. Similar concept on the next two. I'm going to put basically the x and y into this and try to figure out what the question mark must be. So on letter B, something to the -1 power has to equal a half. Well, -1 would mean flip it. This would be the number 2, because 2 to the -1, it would flip and become a half. So the question mark on this is the number 2. This one would be log base 2 of x. And for the last one, again, something to the y, which is a half, equals 3. Again, I'm following this pattern. So to the half power, you can think of that as square root. So the square root of something is 3. That something must be 9. So for this one, I would have log base 9 of x is what y equals. Now, again, obviously they can be more complicated, and we'll see that in some of the graphs coming down here. But on those ones where I'm going to have you figure it out yourself, they'll be the easier versions. So similar to what we did with exponentials, we're now going to graph logarithmics. Same idea, we're going to take the parent graph and do some transforming on it. So on 7a, it's common logarithm. I'm taking the normal function and I'm sticking a negative on the x. That negative is going to cause a y reflection. So I'm going to graph this one in red. It's going to have a y reflect on it. So normally it goes like this. This one's going to go the other way. It's going to flip over the y-axis. So let's actually zoom out just a little bit here. Instead of hitting at 1, 0, it's going to hit at -1, 0. And again, I'm not looking for absolute precision. Something kind of like that. And actually, I have it rising a little too fast, but that's okay. We won't worry about it. It wants the domain and range. Well, on this one, the domain, I'm going infinitely left because it's shooting off to the left to 0. The range is everything, -infinity to infinity. The vertical asymptote is still the y-axis, which is the equation x equals 0. The x-intercept, well, I can see that it's hitting at -1, 0. And I'm going to show how we get that in just a second as well. And since the y-axis is an asymptote, there is no y-intercept. Now, let's say that it didn't hit at such a nice point, like -1, 0. Remember that if I want to find the x-intercept, another way I could have done that is set y to 0. So if I take my graph, or my equation, and I set the f of x equal to 0, I can do loop-de-loop. This is base 10. and say, okay, 10 to the 0 is negative x. 10 to the 0 is 1. If 1 is negative x, then x is negative 1. So remember, we can do that, and we're going to have to do that on some of these. For letter B, now I'm looking at natural log. So we have some transformations. I'll be graphing this one in blue. X minus 2 is going to move it to the right 2. And then negative on the outside is going to be an x reflect. So remember, the point that we're moving is the point 1, 0. That's going to go to the right 2. So I know it's going to hit at 3, 0. And then the graph, instead of shooting up, it's going to be reflected. So it's going to be shooting down and out. So what this is going to end up looking like is hugging the line x equals 2, because the asymptote that was the y-axis also moved over 2, and we're hitting at 3, 0. So domain, on this one, looking at my graph is the easiest thing to do. This thing is going from everything bigger than 2 forever. The range, still negative infinity to infinity. The vertical asymptote moved over 2, so it would be x equals 2. The x-intercept, I can see from the graph, it's 3, 0. And again, I can see that it's not hitting the y-axis. And again, to solve for the x-intercept, I could have also plugged in 0 for g of x and solved for x, which let me show you how that works again. This would have been 0 equals negative natural log x minus 2. Okay, the base is e. If I do loop-de-loop on this, actually, sorry, before I do loop-de-loop, I have to divide over the negative. That's still going to give me 0. So if I divide out the negative, it's gone. Still have 0. So now it's e to the 0. E to the 0 is x minus 2. E to 0 is 1. And so I get 3 for x. Same idea on the next problems. Again, for A, I'll graph this one in red. This is going to be a logarithm, but shifted up 3. I got a plus 3 on it. So again, I have the point that usually hits at 1, 0. It's going to move up 3. So it's going to be at 1, 3. Moving it up does not change the fact that the y-axis is an asymptote. There's no side-to-side movement, so the asymptote's not moving. So if we look at the domain, 0 to infinity, the range, negative infinity to infinity, the vertical asymptote didn't move from the parent, x equals 0. Now, here's where we got to do a little more work to figure out our x-intercept. It's definitely hitting the x-axis. You can see that it's hitting right there, but that's not an obvious number. So we have to say, all right, if I'm hitting the x-axis, set y equals 0. So this would be 0 equals 3 plus log base 4 of x. Before I do loop-de-loop, I've got to get the logarithm by itself. So this would be negative 3 equals log base 4 of x. Now, if I do loop-de-loop on this, 4 to the negative third equals x. And so x is 1 over 64. So my x-intercept is 1 over 64, comma 0. I can see from the graph it's not hitting the y-axis, so again, there's no y-intercept. And by the way, I also know there's no y-intercept if I were to try to plug in 0 for x. You can't do that. You can only take the log of positive numbers. So 0 doesn't work. So that's another reason why I know there is no y-intercept on this. And for the last one, I've got a double reflection. I've got a y reflect and an x reflect. So a y and an x reflect. Again, the y reflect is from the negative inside. The x reflect is the negative on the outside. So think of what your parent looks like, something like this. It's going to flip over the y-axis, which would make it go to the left. And then I'm going to flip that over the x-axis. So the point starting at 1, 0 would flip to negative 1, 0. And then the graph is going to shoot out and back to the left. It'll look something like that. And again, I'm not worried about too much precision on this. For my domain, I'm going from negative infinity to 0. My range, negative infinity to infinity. That's not changed at all yet. And it won't for us, at least. My vertical asymptote did not change. I flipped over it, but it didn't move it. Again, I can see that there's an x-intercept of negative 1, 0. And again, I'll calculate that in a second. There is no y-intercept. And again, to find that x-intercept, I could say 0 equals negative natural log of negative x. If I divide out the negative out in front, I'd have just 0 equals natural log of negative x. If I loop-de-loop, I'd have e to the 0 equals negative x. Well, e to the 0 is 1. 1 equals negative x, so x equals negative 1.